Magnetars are among the most extreme objects ever discovered, and understanding them requires us to go far beyond anything found on Earth. A magnetar begins its life as a massive star, several times heavier than our Sun, that reaches the end of its nuclear fuel and collapses in a spectacular supernova explosion. Most supernovae leave behind neutron stars, ultra-dense spheres only about 20 kilometers wide, yet containing more mass than the Sun. But in rare cases, the collapsing core creates something even more exotic. A neutron star with a magnetic field so strong that it becomes the most powerful magnet in the known universe. These objects, called magnetars, generate magnetic fields 1,000 trillion times stronger than Earth's, powerful enough to tear apart atoms, twist the fabric of space around them, and release bursts of energy that can outshine entire galaxies for a fraction of a second. To understand how such a monstrous field forms, imagine the conservation of magnetic flux. When a star collapses from millions of kilometers across to the size of a city, its magnetic field becomes compressed into a tiny volume. The same amount of magnetic energy is squeezed into a far smaller space, amplifying the field to unimaginable levels. Inside a magnetar, matter is packed so tightly that a teaspoon of it would weigh billions of tons. The magnetic pressure is so intense that the crust of the star, an ultra-dense layer of neutron-rich material, can crack and shift. These crustal starquakes send ripples of magnetic energy into space, triggering powerful X-ray and gamma-ray flares detected by telescopes on Earth. One such flare, observed in 2004 from a magnetar known as SGR 1806-20, released more energy in 1/10 of a second than our Sun produces in 100,000 years, and even disturbed Earth's ionosphere from 50,000 light-years away. Magnetars rotate rapidly as well, often several times per second, but their intense magnetic fields slow them down over thousands of years. As the field weakens and the star cools, the magnetar gradually calms, eventually becoming indistinguishable from ordinary neutron stars. Yet during their active phase, their fields are so strong that they can distort electron clouds, reshape atomic structures, and create conditions that cannot be reproduced anywhere else in the cosmos. Even the empty space around a magnetar is affected. According to quantum electrodynamics, the magnetic field becomes so intense that the vacuum itself behaves like a crystal, polarizing light and altering the paths photons take. Although magnetars are incredibly rare, only a few dozen have ever been confirmed, they offer crucial insights into high-energy physics, matter under extreme density, and the behavior of magnetic fields on cosmic scales. Studying them pushes our understanding of the universe to its limits, revealing what happens when nature takes the familiar concept of magnetism and drives it to such an extreme that the rules of ordinary physics begin to break down.